Hi there, welcome back to this channel and Merry Christmas. Today being 25th of December. All right, because I am taking my time to make a video today, which is the 25th of December, as a Christmas bonus or Christmas gift for me, do well to subscribe to the channel and click the bell notification so that you'll be notified anytime I drop an exciting content like this. And please bear with me. I'm a bit under the weather today, so I might not be able. I will still be able to deliver what I ought to teach you here. Do you understand? But that's why my countenance is like this, by the way. That's what I'm saying. So I said today is Christmas, so subscribe to the channel. All right. Today we're going to be discussing electrochemistry, and basically we're talking about the galvanic or the voltaic cell. The galvanic or the voltaic cell. Now, electrochemistry is the chemistry of how electricity is produced. So, and you see, galvanic or voltaic cells are cells that can produce electricity. And I promise you, you use them every day because they are basically batteries. So whether it's the one you put in your microphone, or the one you use in your torches, or the one you use in your phone, do you understand? They all work on they work by the same principle, and they are called galvanic or voltaic cells. Generally, altogether, we call them electrochemical cells. So galvanic or voltaic cells are cells that can convert chemical reactions into electrical energy. So chemical energy into electrical energy, or they make electricity via a chemical reaction, or cells in which electrical energy is produced via a chemical reaction. All right. So basically, what is electricity first? Now, electricity simply means moving electrons. Electricity means what? Electricity means what? Moving electrons. However, when we'll be discussing the concept of current and all, current electricity, we'll talk about how that it used to be said that conventional current flow from positive to negative. Before it was later discovered that it was actually electrons that moved. All right, so but now we know that electricity is created by moving electrons. Now, in a galvanic or voltaic cell, first the names. Let's talk about the origin of the names. Now, galvanic cell or galvanic or voltaic is from they are names of two scientists who were major. They played a major role in this part of electricity. Is that okay? So this galvanic is named after Ludwig Galvani. Ludwig Galvani. Now I'm going to Galvani. I'm going to create a video where I'll talk about a brief history of electricity, so you will know the impact of both of them in the whole process. And this was named after Alessandro Volta. Alessandro Volta. All right. Now both of them, they were they disagreed on a particular concept known as animal electricity. Now it was Ludwig Galvani that came up with the concept of animal electricity. This is just the introduction. Is that okay? The origin of this whole thing. Now, Ludwig Galvani came up with the concept of animal electricity because he experimented on a frog, and the frog was able to jerk. A dead frog was able to jerk its leg when it connected wire to it. So, because of that, he suggested that animals had their own internal electricity. So, because he said animals had their own internal electricity, Alessandro Volta was against this view, and he said, and he proved it by creating this system, by creating this the first battery in the year 1793. So the first battery, which was known as the pile. the power. Now I'll explain why it's called the power later. So the first battery he created, because it stacked a number of metals toward each other, so they called it the power, and that was Alessandro Volta. But basically, the voltaic cell is a battery. Voltaic cell is what? A battery. So for the purpose of this video, I'm going to be calling voltaic cells majorly, most of the time. All right. Now, what are the components of this voltaic and galvanic cells? What are the components of the voltaic cell? Now, there are two major components. We have two tubes here, two containers here. Now, in both containers, you have in both containers, we'll have what is known as an electrolyte. So we have electrolyte first. Now, an electrolyte is a substance or something that can conduct electricity in its solution. It is a solution or molten form of a compound that can conduct electricity. So molten form, because most of our we call them dry cells. They have pastes. The electrolytes are in form of paste, so we say molten state. So electrolyte is basically a liquid. Is how to think of it as a liquid that can conduct electricity. So the liquid we'll be using here, in this case, it could be anything, because I'm going to give other examples at the end of this video. So the liquid here that will be here is zinc sulfate. Zinc tetraoxo sulfate 6. And here we also have another solution of, this time, copper sulfate. Copper sulfate. All right. Now we could use other metals, and I said that we'll use other examples, but we are going to be using this for now. Now, so these are our electrolytes: zinc sulfate and what? Copper sulfate. Now the second component that you have is the electrode. So these are the two major components, the electrodes. Now the electrode is just a metal that can either accept electron or donate electron. So an electrode here, there are two types of electrode. We have the anode and we have the cathode. So those are the two electrodes we have. Now in this case, our electrodes will be, in this place, there's going to be an electrode that will immerse into this solution. So we immerse zinc electrode in a solution of zinc salt. So this is zinc electrode. And notice it is zinc metal. It is just zinc metal. Zinc metal is immersed in a solution of the salt. And here we are going to immerse copper metal in a solution of its salt also. So we have two electrodes here. We have zinc and we have copper metal. So notice they are not charged because they are neutral. So neutral substances, neutral metals make up the electrode. Neutral metals. Now also notice, now which one is going to be our anode and which one is going to be our cathode? Now, in order to understand that, we must know what is called the redox. Now, redox is the chemical reaction by which this electricity is being produced, and is gotten from reduction and oxidation. So basically, this voltaic cell system, uses reduction and oxidation reaction to create electricity. I repeat, I said the voltaic cell uses reduction and oxidation reaction to create electricity. Now, how does it achieve this? So first, I said, what is reduction? Reduction, now use this mnemonic. There is a mnemonic that will say, Leo, the line goes grr. So grr, like the line is roaring. So we have Leo the lion. Leo the lion goes grr. Now Leo, L stands for loss of electrons. And that is what? Oxidation. Then this gain of electron is what? Reduction. Gain of electron is what? Reduction. Leo the lion goes grr. Is that okay? Now, keep the following in mind. There's another mnemonic I will give you. The other mnemonic is an ox and red cat. An ox and red cat. And standing for anode. An ox standing for what? Oxidation. So what does that mean? It means that what? Oxidation takes place in what? In the anode. And what is oxidation? Loss of electrons. So one will lose electron. So the one which loses electron will be called what? The anode. Do we understand now? And then reduction at cathode, that's your red cat. An ox, red cat. So the one which gains electron. Remember, our reduction is gain of electron. So the one which gains electron will be called the cathode. All right. Having known this, now the next thing we should now talk about is how does this reaction now take place? Now there's one component that I have not added here. There's one component, and that component is the component that this system needs to actually begin working. All right. So and that component is a conductor. So we have this, and a conductor. A conductor. So a conductor, it could be a wire. Do you understand? So we connect using a wire. So and immediately we connect them. The system begins to run. That is, electricity begins to be generated. Now, in a jiffy, I'm going to tell you how the electricity is being generated. But if you remember, we've talked about in chemical equilibrium that a system that works on its own, a system that functions on its own without adding any external impetus, that by itself, it just happens. We say the system is what is spontaneous, or for a reaction in this case, we say it's a spontaneous reaction. So this reaction here is a spontaneous reaction. All you need to do is to connect the wire to the two electrodes, and this system begins to run. So we say it's spontaneous. Just like we talked about the fact that if you put a ball on a hill, the ball, you don't need to push the ball before it begins to what? To roll down the hill. So that is what? Because it's what? Spontaneous. And you remember also that for a spontaneous reaction, we know that the change in Gibbs free energy would be what? Negative. Now I'm just trying to get into all of these nitty-gritties that you will need to understand this concept. And then for a non-spontaneous reaction, you know that the Gibbs free energy is positive. And for an equilibrium reaction, Gibbs free energy is 0. All right, there's also something called electrode potential here. Electrode potential. And now, in order to understand electrode potential, I'm going to be providing what we call the electrochemical series. Now, the electrochemical series comprises of the the metals and also non-metals based on their degree of reactivity. So we have K, NaCa. Let's bring it here. K, NaCa, Mg. I mean, in their ionic forms, we have plus, plus, 2 plus, 2 plus. Al, zinc, iron, tin, lead, hydrogen, copper, mercury, I think Ag and Au. All right. So, okay. So these are now, looking at this electrochemical series, these are the two metals we used as our electrodes. We used zinc and copper. Now I want you to notice something. They are far away from each other, right? Now, so I mentioned something called electrode potential. Think of electrode potential as the difference that they have in electron densities. So you will notice that the zinc, because it is higher in this series, it means it's more reactive than copper, meaning that in a solution, in a reaction between this and this, zinc will be the displacing component. So it will displace copper out of the solution of the salt, if they were reacting together. And why would it do that? It's because zinc has a higher electrode potential, but basically what we need it for is for this Voltaic cell. So what will happen is that because this zinc is higher in the electrochemical series and copper is lower in the electrochemical series, you will remember that this order, as we go down like this, the reactivity decreases. And what do we mean by that? It means that as you go down, their degree of ionization reduces. And what that means is that as you go down also, electropositivity reduces. So it means that these guys up here are more electropositive, and the ones that are down here are less electropositive. Also, it means that the more electropositive you are, the less electronegative you will be. So remember that electropositivity is the quickness, the ability of an atom to donate electrons, electropositivity. So the ability of this guy to donate electrons, of this guys up, is higher than the guys down. So it therefore means that these guys here will donate electrons in a solution involving redox. In this case, the guys up and the guys down have the tendency to accept electron if they are in a reaction, a redox reaction with a metal that is more electropositive, so that they will be as the electronegative component, even though you know that they are electropositive metals. Metals are electropositive, but it's just the more electropositive you are, the less electronegative you are, and the less electropositive you are, the more electronegative you are. So definitely it means that this guy, we have the highest electrode potential. Now, all right, sorry the video was interrupted because the mic stopped working. So I said that this guy, potassium, we have the highest electrode potential. And as we go down the series, we are going to encounter fluorine, which will be the most electronegative element, but we have the least electrode potential. Now, but with an electrochemical cell, we call it cell potential. So the cell potential is measured based on the reduction, reduction ability, or the reduction potential. That's what we call it. I'm trying to use the term for it. We call it the how easy it is for an electrode to be reduced. That's what I'm trying to say. We measure cell potential, which is actually electrode potential, more like saying that, you know, water flows from a high potential to low potential. Okay, so because water flow, that is thermodynamically speaking, where we talked about gives free energy, and I'm going to relate E cell. We're going to relate E cell with electrode potential, the gives free energy soon. But I want we said the electrode potential of a cell is called the cell potential. So just like water flows from high potential to low potential, electric current here also flows from high potential here, which is in the zinc, to low potential in the copper lattice. the copper electrode. All right, so we measure this cell potential by the degree of reducibility, so to say, that is how easy it is for these metals to be reduced. Remember I said the gain of electron is what? Reduction. So how well or how easy it is for these metals to gain electrons. Do you understand? So this metal is the one gaining electrons, so we say it is reduced. This metal is the one giving electrons, is oxidized. But we measure the cell potential as reduction potentials, reduction potential. So there is a formula for cell potential. The cell potential is given by E cathode or E anode, anyone, plus E anode. And we already said that this E cathode will be what? Reduction potential at the cathode, and E anode will be the what? The reduction potential of the anode. Just follow me. Now I said E cathode will be what? The reduction potential of the cathode of the electrode, which is the negative electrode, and this one, the reduction potential of the positive electrode. Now, remember I said that we used an ox, red cat, an ox, red cat. Now, you see, an ox is showing that, means that at the anode, oxidation takes place. So if at the anode, oxidation takes place, how do we now record the reduction potential? Now, we know that oxidation and reduction are basically reverse processes of one another, so that you know that loss of electron is oxidation and gain of electron, which is just a reversal of the process, right? So it means that E cathode is basically negative of E anode. Do you understand? E cathode is basically what? Negative E anode. That is, the reduction potential of the anode is of the cathode is just negative reduction potential of the anode, because we know that oxidation is what takes place at the anode. Oxidation takes place at where? At the anode, and reduction takes place at the cathode. But in order to understand, because we represent it by reduction potential, keeping in mind that the zinc is not being reduced. So if it is not being reduced, then it means it will be negative of what is happening to it. Do you understand? Just the way we say that if a substance is going up in physics, we say that the substance, if something is moving up, we say that it has negative G, moves up with negative G. And when the substance is coming down, G is positive. So the same way, because it's doing opposite of what acceleration, what gravity would normally cause a body to do, going up. That's why it's negative. So the same way here, we know that the anode is not being reduced because it's the one giving electrons. So we say that it is negative reduction potential. Do you understand that? So what does that mean? That means that E cell will now be equal to E cathode minus E anode. E cathode minus E anode. Now I'm going to still reiterate this in order for you to understand it well. Well, let's now go back to this thing and know our electrochemical cell and know how the process of electron exchange takes place. Now, how is the electricity being generated? Now, this is what happens. Now, notice, we said that once you plug this wire on the two electrodes, something very important, something very unique begins to happen. And what is that thing that begins to happen? Now, electrons will begin to flow from these zinc plates to the copper lattice. Now, this copper plate will begin to take electrons, gain electrons, while this guy will be what? Losing electrons. Keep in mind, I said at the beginning that zinc plate is made up of basically zincs, neutral zinc atoms. They are uncharged. While copper plate is also made of what? Copper atoms, neutral copper atoms, uncharged. So, but in the solution, what do we have? In the solution, because the solution is a solution of copper sulfate, we have Cu2 plus, Cu2 plus ions, Cu2 plus ions, Cu2 plus ions, Cu 2 plus ions and SO4 2 minus. Is that okay? So you see that I'm putting less SO4 2 minus because our emphasis is on the metals. Now, here in the solution also, because the solution of zinc salt, we have zinc 2 plus ions, zinc 2 plus ions, zinc 2 plus ion, zinc 2 plus ion, zinc 2 plus ion, zinc 2 plus ion. Now, and of course, SO4 2 minus. Now, what do we have here? Because, I mean, if you don't understand what I did here, I simply ionized this. That is zinc SO4. We ionized to form zinc 2 plus and SO4 2 minus. And copper sulfate, we ionized to form Cu2 plus SO4 2 minus. All right. So that's why I came about this. I came about these ions. You know that by Arrhenius' principle, it says that substances ionize to form freely moving charged particles called ions. So these are freely moving charged particles there. All right, so now what happens? From this metal plate I reiterate, this metal plate, a particular zinc, so let's pick the first zinc atom here. The first zinc atom here will lose electron, okay, because this side is not in the solution. So let's pick the side that is in the solution. So nothing will happen to this guy that is not inside the solution. Is that okay? So what will happen is that this first guy in the solution will lose 2 electrons. And why is it losing 2 electrons? You remember when we ionized, we said that from the ionization, you know that it is divalent. It means it has 2 valent electrons. So it will lose 2 of its electrons. And as it loses 2 of its electrons, the 2 electrons will move out towards the copper plate. So 2 electrons will move in this direction, 2 electrons will flow in this direction, 2 electrons will go here, and go here, and go here, and will enter into solution here. So we'll pass through this guy. We said this is an electrode that allows the electrons to pass through. So this electron, this 2E minus, will pass through and come into the solution. So once it gets into the solution, copper ion here, which is ionized, Cu2 plus, will gain the electron. So once it gains the 2 electrons, remember, positive will cancel negative, and then what will happen? We have Cu metal, copper metal. So this guy will gain this electron and become ordinary Cu and will come and join this copper lattice. So a particular copper ion has joined the copper lattice here, and then you have noticed that the copper has even increased in size. But the basic thing is understand first that 2 electrons are going to leave here. So this guy has left this zinc lattice here, these zinc plates. So then we have that zinc, another zinc again, will lose 2 electrons the same way, and another copper in another half cell reaction. Now these 2 cells are called half cells. They are called half cells. Half cells, both of them are called half cells. Now, what is happening here? A gain of what? Electron. So we call it reduction half reaction. We call it what? Reduction half reaction. Then this guy is losing 2 electrons here. So now I'm going to show you the simplest way to write this. Since we say it's losing 2 electrons, and we said loss of electrons what? Oxidation. LEO, L-E-O. Loss of electrons oxidation. So zinc, now just bear with me first, will lose. Lose is like minus, right? Like negative. Minus 2 electrons, right? To give you what? Zinc 2 plus. Isn't it? That's what we said. It will lose 2 electrons and will come and join this solution and become zinc 2 plus. Now, you know in chemical reaction, we don't use negative, we use positive. So what will you do? Carry this guy over to this point. So it will become a positive, or you add it to both sides, either way you want to think about it. And zinc will become zinc, zinc ion, zinc metal will become zinc 2 plus 2E minus. Do you understand this? We use a negative. Now, I'm using a negative to denote it for you so that you understand that it is a loss. Is that okay? Now, another way to see it is, once you see, because in JAMB questions, you see things like A chemical reaction will be written for you, and then you'll be asked which one is oxidation and which one is reduction. The trick is this. Once you see the electron on the right-hand side, that is oxidation. So when you see electrons on the right-hand side of the equation, oxidation, you see electrons on the left-hand side of the equation is reduction. Do you understand that? All right. About the easier way to explain this is that zinc, two electrons are being lost here. So because it's losing two electrons, they will carry just to become positive, and then we have what? Oxidation. So we call this oxidation half reaction. Now, in order to have the full cell reaction, the complete cell reaction, we now combine both reactions. So we have oxidation half reaction and reduction half reaction. Let me clean our electrochemical series. So I said that the oxidation half reaction is zinc to become zinc ion plus 2 electrons, and reduction half reaction Cu2 plus 2 electrons to give copper metal. So what will happen is that because they are on the opposite sides, these 2 electrons will cancel each other. I mean, you know that species that appear the same way on both sides of the equation always cancel out. So we now have that this is on this side, so that is zinc. Now this is what we call cell notation. We call it cell notation. Now the way a cell notation is written is we separate with bars like this. We separate with bars. And the reason for separating with bars is basically for 2 reasons. That's one, the first one is that the 2 guys are happening in different, they are separated in different electrolytes. You understand? So they're only connected by a wire. So we are separating by bars, with bars. So this guy is on this side, copper 2 plus is also on this side, Cu2 plus. So then we now use double bar to show that this is the forward reaction, this is the backward reaction, and this is the forward reaction. Or this is the later reaction, like this is the latter reaction, this is what will become of them later. So plus Cu. All right, so this is the overall reaction, or cell notation. All right, now this is not all, but I hope that you have understood that electrons will be lost from here and they will be flowing into here immediately to connect the wires. And over time, that process will repeatedly occur and occur and occur until most of this zinc has been eaten up and have joined solution. Remember, once they lose the electron, they will become zinc 2 plus and join solution. They lose electron, they lose electron, they become zinc 2 plus and join solution. Okay, yeah, I wrote it there. They lose electron, becomes zinc 2 plus. They lose electron, becomes zinc 2 plus. So they keep losing electron and becoming zinc 2 plus electrons. While on this other side, these guys keep taking up electron and become part of the lattice. Take up electron, become part of the lattice. Take up electron, become part of the lattice. Take up electron, become part of the lattice. So, and over time, you will see that there is a noticeable change in the lattice, the copper lattice. It has become fatter. What has happened to our zinc lattice here? It has become what? Smaller. So the zinc plate has been eaten up because it has lost zinc ions. Do you understand now? So by losing those zinc into the solution, what will now happen over time is that this guy, however, it's a short period of time, but you'll notice that this solution will contain more positive ion, and this guy, because of the removal of positive ion, it will be saturated with what? Negative ions. Are you following me? This guy will now be saturated because it's already Cu2 plus CuSO4 that is inside the solution. So, but because Cu2 plus keep leaving the solution and joining the copper metal, this guy will now be saturated with, will now have more higher concentration of SO4 minus. But here we have a greater concentration of what? Zinc 2 plus ions. So what does that mean? There will be a polarization such that there is plus, this place is now positive and this place is now negative. And because of that polarization, this system will not be able to run for too long. Now, the way, one measure that is used to circumvent this or to salvage the situation or to the solution to that problem is that we use what is called a salt bridge. We use what is called what? A salt bridge. Now, what is a salt bridge? A salt bridge is basically one other long pipe. Are you listening to me? Now, one other long pipe that contains a solution of, positive and negative ions in which, so we could use, for example, we could decide to use Cl, potassium chloride, or let's use potassium we can even use aluminum sulfate or aluminum nitrate, or I want to use something. Okay, we can use silver nitrate. So we use silver nitrate, for example. So if we are using silver nitrate, then what will happen is that, so inside this solution, this salt bridge contains silver nitrate, for example, or silver chloride. Just use any electrovalent compound. So Ag2+, Ag2+, like that. You have them many in the solution. And then you also have NO3 minus, NO3 minus, NO3 minus, NO3 minus, that way. So now, what you will see is that now there is Ag2+. Now, what the salt bridge does is this. These are salt bridges containing silver nitrate. Now, what the salt bridge will do is this. Now, you see, because positive charge is being built up here, in order to avoid that polarization, what will happen is that the negative charges here, NO3 minus, will come here to come and neutralize the building up of that, what? Positive charges. So it will form zinc nitrate here, and then we'll make space for more oxidation to occur with these plates. So nitrates will come here because it is positive charge that is building up here, and nitrate is negative, so nitrate will come here. Then silver ion will now come here because negative charge was building up here. So Ag2+ will come and neutralize the effect of that thing. So that is what, and it happens by itself. They'll be attracted. Just it happens by itself. It's not the experimenter that will do that. Once you make that solution available here, what will happen as this reaction begins to run is that as positive charges are building up immediately, the negative charges will be coming here, and the positive ions will be coming here, cations. We call them cations, positive ions, and we call negative ions anions. Do you understand? So anions will be coming here, and that makes sense because we already said this is the what? This is the anode. So anions will come here, which are what? NO2 minus, and cations go to cathode, which are the positive ions. So they go to the cathode. Now, in the absence of that salt bridge, this system cannot run for long because the system will be polarized and there will be no continuous flow of electrons. Now, let's now get to the cell reduction potential that I talked about the other time. Now, the reduction potential. Let me re-explain what I said. I said that reduction potential is just how we denote the extent of reducibility of a metal. Now, we do know that these metals cannot gain electrons or do not naturally want to gain electrons. But we represent, especially for zinc in this case. In fact, zinc has what we call reduction potential of minus, the reduction potential is represented in volts. The reduction potential is represented in what? In volts. Zinc has a reduction potential of minus 0.6 volts, while copper has a reduction potential of plus 0.34 volts. Now remember that I said that the electric potential of a cell or cell potential is given by E cell is equal to E cathode plus E anode. But we know that at the anode, it is oxidation that occurs. So it means that at the anode, reduction, we said is oxidation that occurs, not reduction. So, but we know that reduction and oxidation are reverse processes of each other. So we say that E anode is just negative E cathode, or E cathode is negative E anode. E cathode here. Do you understand? It's just a reverse process, as in E reduction This is what I'm trying to say. E reduction or E oxidation, which is what takes place at what? At that node, is just equal to, or E reduction is just negative E oxidation. Do you understand? So what this means is that you know that it is oxidation that takes place at the anode. So in order for it to look like reduction, we just add minus to show that it is the reverse process of reduction. So what now happens is that since this is E anode, then E anode will be negative. So that our E cell will therefore be equal to E cathode minus E E anode. Do you understand? So the formula for E cell or cell potential of a particular electrochemical cell will be what? E cathode minus E anode. Now, if we want to calculate for our electrochemical cell here, let's calculate the electric potential for it. E cell, therefore, in this case, will be equal to, what's our E cathode? Our cathode is copper. If E cathode is positive plus 0.34 volts, then minus E anode. E anode is minus 0.76. That is minus 0.76. So all in volts, right? All right. So we have 0.34 minus times minus plus 0.76 volts. All right. So by the time we add this, so we have 0.76 plus 0.34. We have 0 here. We have 1 here. 1.10. All right. So it means that E cell for this guy, for this electrochemical cell or voltaic cell, will be what? 1.1 volts. So, and that is, so if you see our battery, the common Tiger battery that we use here in Nigeria, you're going to see, if you look at the label on the label, you're going to see 1.5 volts. So the 1.5 volts here, there is the E cell of that battery, 1.5 volts. It means that the electropotential, the difference in potential between the two electrodes inside that small battery is what? 1.5 volts for the case of our small Tiger battery. While this one is 1.1 volts. So the difference in their potentials is what? 1.1 volts. And that's why what? Electron is able to flow from here down here. All right. So that will be it for this video. That will be it for this video. We already know how to. Okay, I also said I was going to talk about the fact that we could use something else here. Because there are some problems. So I mentioned one already. One of the problems of this voltaic cell. So this is a primary cell first. Know that. There are two types of cell. We're going to get to that in physics, in the physics of this thing. There are two types of cell. We have the primary cell, the primary cell. Let me clean everything we have here. But understand the fact that this guy has eaten up and this guy has become bigger. And it is a physical change that will occur there. A physical change that you're going to notice. All right. Now, I said that there are two types of cell. We have the primary cell and the secondary cell. The primary cell and the secondary cell. Now, the primary cell is so called because it cannot be recharged, unrechargeable. And why cannot be recharged after use is because the anode is completely used up. The cathode is completely used up. And what charging does is basically to replace the anode that is being used up in the electrochemical process. Do you understand? So a primary cell is unrechargeable because the anode is used up completely, and an electron cannot be redeposited to make up the anode again. That is why it is unchargeable. While secondary cell can be recharged, so rechargeable. So, and a typical example of primary cell is the voltaic cell that we just talked about. The voltaic cell, the Daniel cell, the Leclanche cell, and so on. But secondary cell, we have the lead acid accumulator, nickel, cadmium, and those other examples. But now, my point is the problems that these electropotential of these primary cells, we have polarization. There are two basic problems. We have polarization and local action. Now, I'm going to make a video that will explain this in detail, but for now, let me just explain briefly so that you know what they are on the preface at least. Now, polarization is when there is a setup of two different, just like we had in this case, there is positive charge in one end and there's negative charge, and because of that, there is no flow of what? There will be no flow of what? Electrons again in that direction. So that's polarization. Now, another way polarization can happen is if we had used, for example, if we had used H2SO4, for example, as our electrolyte, because in the original Voltaic cell that was made by Alessandro Volta, H2SO4, we know I called it the pile just now. Pile. That was the battery he made. And that was because he stacked upon each other zinc plates. He put a copper plate, and then followed by a zinc plate, followed by a zinc plate, and then followed by a copper plate. Then in between, he soaked a paper with H2SO4 and put it in between, so the electron can flow with that will serve as the electrolyte. Then so he puts copper, zinc, copper again, zinc, like so. He said copper, zinc. So that was how he stacked them upon each other like that to be much, so that the voltage that will be generated will be higher. So that was how I created it. So that's why I'm using this example here now. So, and I still had my zinc and my copper. Then I connected it with the battery. And so what will happen here is that, yeah, the same way. Well, you know that here we have H plus and H2SO4, H plus and H2SO4. The same thing will happen. Zinc will begin to lose electron into copper. But what will happen else? What else you see happen is that as electrons are being deposited here, what will be gaining electrons here is hydrogen. So hydrogen will gain electrons, and once it gains electrons, it becomes what? Hydrogen atom. And once it gains electron, hydrogen is H plus, sorry. H plus will gain one electron, will become this. So two hydrogen atoms, two hydrogen ions will gain 2 electrons, will become this. Now, to balance this, you put H2 here to form H2 gas. But the best way to write this reaction is to say H plus will gain 1 electron, 1 H plus will gain 1 electron. That means separating them will become H plus. Another H plus will gain another electron, will become H plus. So H will now molecularize to form H2 gas. Do you understand? So, but this is the simplified reaction. Now, what I'm saying is this, that hydrogen gas will be the one that is formed here. And that hydrogen gas, some of them will be evolved out of the solution. Now, as some of them are being evolved, some are not being evolved. So some will now come to the surface of this thing and attach to it. Some will come to the surface of this thing and attach to it. And because of that, now remember that when we use copper there, then copper attached to this and did not cause any other reaction. Is that okay? Remember that polarization was stopped then using a salt bridge, right? But in this case, because of hydrogen bubbles that are being formed here, there will be another system here because of difference in reduction potential between hydrogen and copper. Because by standard reduction potential, hydrogen is used as a standard. We call it we call it hydrogen. Just so that hydrogen reduction potential is taken to be 0. Do you understand? So because it has 0 reduction potential, and this guy, copper, has minus plus 0.34, as we said, then you will see a back EMF will be will be generated. So that back EMF will negate the direction of flow of electron, which was directly here before. So there will be a back EMF generated between the hydrogen gas that is attached to this and the copper plates. So that back EMF will negate the direction of EMF that was generated before. So that is polarization. That is polarization. Now another thing that we will see happen. So a way of doing this is to put a vacuum that can absorb hydrogen gas, remove them from solution, or use a depolarizer. Now, for local action, what happens with local action is because of possible impurity in the plates. So, for example, zinc plates, the commercially sold zinc plates usually have impurities. So they contain impurity, and those impurities, even after you have removed this system, if you leave this in solution, those impurities will still be generating electricity. Like it will set up an EMF even in the system itself. So, and that, that that uses up the zinc. It uses it up quickly. Do you understand? So that's local action. So one way to correct that is by a process known as, so I said here use the polarizer, use the depolarizer. Then for this one, use amalgamation. So by amalgamating, so when you amalgamate by using mercury or any other, but basically they use mercury. But I think you can use other metals to coat the zinc, so that when you cover the zinc up, so the process will be unhindered and impurities will have no effect on the zinc electrode again. So by amalgamating or coating with another metal, we can solve that problem. So that will be the end of this video. I pray that you pass all the exams that you're preparing for, which is one of the reasons why you might be watching this video. Do want to subscribe to the channel. As I said, this is my Christmas gift for you. So just give me a Christmas gift too by subscribing to the channel. See you in other videos.